Hello, honors physics students. Please make sure you have your light practice problems in front of you. We're going to start with problem 28, so go ahead and read problem 28, pause the video, sketch out the situation, draw the boundary between the two media, draw the normal, draw the light rays incident and refracted. So you really want to try to visualize what's happening here, make your prediction as to which way light is bending, label the angle that's given, then come back to the video to make sure you've drawn the problem correctly. So this problem is really important that we draw the problem correctly, we draw the situation correctly, because otherwise you're going to be visualizing incorrectly. You might even get the right answer, but it doesn't really matter because then it's not going to make sense when you actually draw what actually happens. So here's what actually happens. We've got Heather underwater here represented by this circle. Couldn't draw all the parts of Heather, just there's her head. Here's the island, and here's the palm tree she's looking at. Here's the water, and here's the normal to the boundary. And so the first question is, which way is the light going? Is the light going from the palm tree to Heather, or from Heather to the palm tree? Well, if Heather's seeing the light, light is coming to her. That's how we see light. Light comes to us. And so immediately you may have to completely change your picture in the direction of the arrows, because light is going towards Heather from the palm tree. So does that mean light's going from the air into the water, or water into air? Well, light's going from air into water. So then you ask yourselves the usual question. Does that mean the light is speeding up or slowing down? Well, if it's going to water, it's slowing down, right? Going to a more dense medium. And then is it bending towards or away? Well, if it's going to a slower medium, it's bending towards. And so our picture should look like this. Light's going from the tree in the air into the water, bending towards normal, going in this direction. And if your diagram is incorrect, you've got to pause the video now and change it, because it is important that you visualize what's happening. It's also super important you're drawing arrows on your rays. If I draw arrows, you draw arrows. You have to be able to see which way light's going to make an accurate prediction. Okay, so how about this 37 degrees? Well, that's the angle that Heather sees the light at. So is that in the air, or is that in the water? Well, since Heather's in the water, that means that that angle is in the water as well. So the 37 degrees is there. Again, if you got that wrong, you've got to pause the video, you've got to fix it, and then you may have to redo your problem. Now, you know you have the right answer there, so you know if you're getting it right, but still, you maybe have been visualizing incorrectly, and so it doesn't matter if you're doing it right or not. Okay, so there's 37 degrees. Is this theta 1, or is this theta 2? Well, here's where it's so important you've drawn the arrows correctly. Light starting in the air and going to the water, 37 degrees is in the water, that's theta 2. So what are you actually solving for? You're solving for theta 1. Where again, you may have gotten the problem completely correct. You got the right answer, but if everything's backwards and you're drawing things wrong, you're still not getting it right. And so it's not just about getting the right answer, you have to know what's actually happening. So if you're doing any of this wrong, you have to pause the video, you've got to redo it, you've got to draw your arrows correctly, you've got to be solving for the correct thing. Okay, so from here, it is just straightforward. It's Snell's law, you have no problem getting the correct answer. But before we move on, what are the implications of this? Well, see, here's what happens, is that light changes direction going from the air into the water, and Heather only sees the light going through the water. As humans, it turns out when it comes to light, we're kind of stupid, as I say. We're easily fooled. And so we have no way of thinking of light other than it's coming to us in straight lines. And so Heather thinks the light is coming to her in a straight line here. She can't possibly understand that it's changed direction going from the air into the water. So if we redraw this picture and sort of trace light backwards, Heather thinks light's coming in a straight line like so. And so she will see an image of the tree all the way up there, elongated. And if you've ever been underwater and you look up through the water at something outside of the water, this is something that you'll see. You'll see that everything appears to be farther away. It's really just a trick of the light. The light has changed direction going from the air to the water, but our brains can't understand that. So we naturally interpret it as coming to us in straight lines. And so we see an image that's farther away from normal. Okay, so we're going on to problem 29. Go ahead and same deal, read the problem, draw the picture, draw a very carefully drawn picture showing which way light's going, what direction, draw all the arrows, label any angles you're given, then come back to the PowerPoint and see if you've done it correctly. So once again, the question is light going from the fish to Spencer, the cat, or from Spencer to the fish? Well, we're focusing on Spencer, right? Light's going towards Spencer. Light is starting in the water, going into the air. So here's our general picture. Here's the boundary between the water here and the air there. This circle represents Spencer. This is my great picture of a goldfish. Okay, and so we've had to light going from the goldfish to Spencer. So Light's going from air into water. Is that speeding up or slowing down? That's speeding up. So does that mean light's bending towards or away from the normal? It's bending away, right? And so again, if you've done any of that wrong, pause the video, redraw your picture, and make sure it's done correctly. So it should look like this. It's going from the goldfish out into the air, bending away from the normal to get to Spencer's eye. Alright, so where's this 28-degree angle? Well, that's the angle that Spencer thinks light's coming to him from. And so is that in the water and the air? That's in the air. So is that theta 1 or theta 2? That's theta 2, right? Follow the arrows. Light's going from the water into the air. This is the second medium. The 28-degree angle is up here in the air. And once again, if you've done any of that wrong, you've got to pause the video, you've got to redo it, and then you're going to have to redo the problem, possibly. I keep referring to that, even though if you're getting the problem right, that's fine, but if you're not visualizing correctly, you're really not getting it. And, that's a matter of interpretation. You have to be able to read the problem and draw a correct picture from that problem. So what are we actually solving for here? We're solving for theta 1. That's the angle, the true angle the light makes with the normal in the water. And so you may have to redo it. But once you do, you should be getting the 20.7 degrees. Just a matter of doing Snell's law. Alright, now go ahead and read part B. Pause the video, see if you understand what's happening, then come back to the video, and I'll go through it. Alright, so here's the idea. Spencer, just like people, is stupid when it comes to light. So Spencer thinks light's coming to him in a straight line, so we would naturally trace this light ray backwards, and so Spencer sees an image of the goldfish up here, closer to the surface, by tracing this light ray backwards, because he thinks light's coming in a straight line. And let me just digress for a second. This is the classic example of refraction we're all familiar with when you put a straw in a glass of water, right? You put a straw in a glass of water, and from different angles, it looks like the straw is bent. The straw is not bent. Of course it's not. It's a trick of the light, because when it comes to light, humans are stupid. That's right. We're stupid. That's all that it is, right? And so the end of the straw would be represented here by the goldfish, right? So the end of the straw is really down here, but because the light changes direction going into the air, your brain naturally traces backwards. So you see the end of the straw over here, closer to the surface, and the whole straw appears bent. Like the straw would be here, and then bent, or it appears bent in the water, because the image of it is all the way up here, closer to the surface. And you can see this anytime you're in the pool and you're looking down through the water at something, everything looks closer to the surface. You're seeing an image of that object. Okay, so what are we really trying to find here? Well, Spencer thinks that the image of the goldfish is 6.5 centimeters down below the surface. But here's where the goldfish actually is. So our job is to find this actual distance from the surface down to where the goldfish is. We can call that, I don't know, D for depth. To make this problem a little bit easier, we'll assume that there's no difference in how far away the goldfish appears horizontally. It's just a vertical difference here. And so it's really just a matter of drawing some good triangles. So one triangle would be here. Here's the apparent depth of the goldfish, and we'll call this distance x, represent the horizontal distance from the normal over to where the goldfish is. Here's a second triangle representing where the goldfish actually is, some distance down here, lowercase d, and the same distance x away from where the normal is. So see here if you can figure out where the angles belong in these triangles, and then how you could solve for lowercase d, assuming that this x is the same as this x. Pause the video, try it on your own, and come back to the video to see how I do it. Okay, so hopefully you should be able to see this triangle up here represents where the image of the goldfish appears. And so this angle is the one we're looking for to label on the diagram here. You should be able to see that's the 28-degree angle. Here's vertical angles. Here's the normal. Here's this line traced backwards. This angle 28 degrees is the angle 28 degrees here as well. So what's this angle over here? Well, that's this angle here, the true angle of the normal. That's the 20.7 degrees. So the question becomes, how are we going to relate all this? Well, it should be a trigonometric function. If you haven't figured it out yet, pause the video and see what trig function relates to these terms. You should be able to see, looking at this triangle, we know this information, this side of the triangle here, that is the tangent function, right? Tangent is opposite x over adjacent, that's 6.5 centimeters. By the same token, we could say tangent at 20.7 degrees is this opposite x over this adjacent d, which is what we're looking for, and then you can either solve for x using this triangle here, then plug it back in, or if you're kind of savvy about it, set the two x values equal to each other, bypass the need to even find x, and we should be getting the answer there of the 9.16 centimeters, or possibly 9.15 centimeters, depending on some rounding issues and how you went about solving the problem.